Good afternoon. I'm Jill Pfeiffer, and it's my pleasure as president of the AMS to welcome you to the first of the 3 Colloquium lectures. Our speaker is Ingrid Daubechies, the James B. Duke Distinguished Professor of Mathematics and Electrical and Computer Engineering at Duke University. Ingrid Daubechies has made fundamental contributions to the theory of wavelets, fundamental discoveries in the theory of wavelets, including the first examples of wavelets that are continuous and compactly supported, and played a critical role in making wavelet methods a basic tool of applied mathematics. She's made major research contributions to many areas of the mathematical sciences, in analysis, in biological modeling, geometry, and mathematical physics. Ingrid Daubechies received her PhD in 1980 in Brussels, where she spent the first few years of her career. She's been recognized with many significant academic honors and awards, including membership in the National Academy of Engineering, membership in the National Academy of Sciences, a MacArthur Fellowship, AMS Steele Prizes in Exposition, and also seminal contribution to research. And her career has included many firsts for women. First woman to be full professor at Princeton in mathematics. First woman to be president of the International Mathematical Union, and first woman to receive the National Academy of Sciences Award in mathematics. In her professional life, she is also well known and recognized for her work to expand access to mathematics and science in developing countries, for work to break down barriers for women to fully participate in science, and for her enthusiastic mentorship of students and early career researchers. So it's truly a privilege to introduce her lecture today, entitled Mathematical Frameworks for Signal and Image Analysis. Welcome, Ingrid.
Thank you, and it's a pleasure to be here. I hope my voice will last the whole colloquium series. I've had a very bad cough and cold, so I'm lubricating it as we speak. Okay, I would like to dedicate this presentation to Alex Grossman, who was my mentor and who sadly passed away last year. I learned a lot from him, not just mathematically, but also in ways of appreciating mathematics and life. So we have 3 lectures, and I will visit in each of those lectures. We will center around one particular application field. This one will deal with images and other data that have content at multiple scales. Well, as you can see, images, as you make them blurrier, they still have content, and so you do see that fine scales, coarser scales, and so on all have content in the image. Tomorrow we'll talk about what happens when an object like this is present but lives in 500 dimensions and you have no idea, and what you get are samples, noisy samples of this object. How are you going to discover that that object is there and its properties? And on Friday, we'll talk about simultaneous time-frequency analysis. And you'll discover what I mean by that and how we can do it. In all of these cases, I am going to focus on, there are many different aspects, but I want to highlight one or several insights that make a real difference and that are mathematical insights, because I believe that, my way of doing applied mathematics has not been to just prove theorems about certain type of very applied objects, but try to gain real mathematical understanding of an area, of a problem area, and then use that insight in order to be able to deal better with those data. I will also make a shameless and proud application of this opportunity to highlight recent results by my students and postdocs. So every one of those lectures will have one. And I will not typically do many technicalities. I will use pictures. A picture, I had a colleague at Bell Labs who said a picture is worth 1,000 words, but only if you have those 1,000 words. Now, I can guarantee you, I have the 1,000 words in all these cases, but I'm not going to give them to you, but you're welcome to seek them out afterwards. And now I stop for a commercial. My commercial is about a recently started program by the Friends of the IMU, a program for the IMU by the Commission of Developing Countries that's called Graduate Research Assistantships in Developing Countries. It's been, since 2017, we have been giving fellowships. It's a modest program. The program is for countries where the need is greatest, so the very poorest countries. Countries where the stipend that we offer, which is $3,500 per year, is sufficient to actually make it possible for a student to concentrate on mathematics and not to have to do it after they do 2 other jobs. And we find advisors that have international collaboration, where the international collaborator is really engaged in making sure that there is a connection between this group and the larger math community. And we try, when we can, to have a small cohort rather than one student, because we all know that we learned a lot from our peers when we were in grad school. So if you want to find out more about it, this is the URL, friendsimu.org grade, and you can also find it at the IMU webpage. And just think of it, $3,500 per student per year. If 10 mathematicians contribute $1 each day, that gives us a graduate fellowship. So consider it, please. We now return to the main content of this lecture. Wavelets and beyond. Let's look at an image. I mean, a digital image. Let's look at, we blow it up, and we have these gray values. And if you can think of that as just a function on a rectangle, a function going to 0, 1, where 0 is black, 1 is white. And, or of course, it's going to be a sampled function in general. It can be also a locally averaged function. What is typical about these functions is that they clearly have very sudden transitions, as you can see. I mean, yes, here, sudden transitions on there. There's noise. I mean, there's never anything flat, it's always, but you have very smooth parts too. Sound actually is something similar. Here is a little bit of speech. And again, you have a function now of one variable where you have sudden transitions. Again, here, all of a sudden, a new word starts, and it's noisy. And you have, in this case, some high-frequency parts that are very smooth. So we want to look at transitions in time, and we want to localize in frequency if we think in one variable. And of course, this is something that may seem at first something that we cannot do mathematically, but it's something we've been doing for ages. Music notation does exactly that. It tells musicians what notes, so frequency information, to play when. We do that more modernly in spectrograms. Here's a spectrogram, and we'll see a little bit more about spectrogram in a few minutes, of a piece of music. Here is a similar spectrogram of a piece of speech, and you see those characteristic times in between where not much is said, and then all of a sudden things start up again. And that's shown by these rainbow colors, and you see clear structures. Frequency is vertical here, time is horizontal, and the colors, high intensity is red, low intensity is blue, indicate presence of information. And here you even have a spectrogram on which people have tried to automatically assign nodes to do automatic frequency reading. Okay, time frequency localization. Let's do it a bit more mathematically. So let's start with a function that is a square integrable. We look at its Fourier transform. We assume that it's well localized in both time and in frequency. I mean, around a certain average. So the average time is of some tau f, average frequency is some nu f, and we can, for all practical purposes, for all signals of interest to us, we can typically consider some large box so that outside the box not much happens. So most of the things are localized around that central time and around that central frequency. That can be a big box, but that's what you saw on those spectrograms. So you can then talk about time frequency localization by taking your signal f, multiplying it by a nice window that's nicely localized in time, and move that window around, and modulating it. If you look at the Fourier side of this, this formula via the unitarity of the Fourier transform is equivalent to the next one, which says that you also nicely localized in frequency around nu, if W had the Fourier transform of the window is nicely localized. And so you have something that takes a little bit of nugget information, nicely localized in T and nu, tau and nu, and then you move tau and nu around. And it's by looking at the absolute value of that quantity that people make these spectrograms. And so you see there's certain frequencies at certain times where you have a lot of information, others where you have very little. So they pull these two variables apart in this windowed Fourier transform. From the windowed Fourier transform, you can reconstruct your function nicely via this integral. So you have the windowed Fourier transform. If you then take your window and you take a kind of inverse transform, you reconstruct your f. So you have all these little nuggets, and together they make f. Very reasonable. You might want to discretize this. So instead of looking at translates by continuous time, continuous tau, you do it by certain jumps. You do the same in frequency. And for an appropriate window function. And you may then ask yourself, can I have a nice orthonormal basis? And of course you can. I mean, you can, for instance, say, I will just cut my signal into pieces, and on every one of those pieces I will compute a Fourier series. That's a windowed Fourier transform, and of course I have a unitary map from one to the other. But it's not very good time frequency, because your window, this rectangular window, has a very bad decay in frequency. So in frequency, I'm not very well localized by doing this. You could do, of course, because we had this symmetry in the formula between time and frequency, you could do the same in frequency. I could chop in frequency, and then I will have very bad decay in time. So in both situations, I'm doing very well in one variable, but not so well in the other. So the real question is, do there exist windows for which we can make an orthonormal basis that has good time frequency localization properties? And, And for instance, I could ask if I want at least quadratic decay in time. Typically, you want much better than that, and quadratic decay in frequency. And even though these are very mild conditions, the answer is already no. You can't do that. And so I'm going to sketch a little bit the argument of why you can't do it, because I'd like you to get a little bit of insight in that hurdle. Okay, so I was looking at things that were discretized by hops in T, and frequency was discretized by hops in omega. I'm going to look at just hops that are integer, and as we'll see in a little bit, the hop in frequency, if you want an orthonormal basis, then has to be a 1 as well. So this is capital T and capital omega, both equal to 1. And this is the theorem that if you have an orthonormal basis, then it has to be badly localized, either in time or in frequency. As I said, we can cover the general case by just scaling. So what if T times omega is not 1? So then I cannot scale both of them to 1 at the same time. Well, what happens is that if you have too few of them, so T times omega is bigger than 1, then in fact you can find functions that are orthogonal to all of them. So you can give up hope to have an orthonormal basis. And if you're too small, then you have too many functions. We'll come back to that. To show to you that I have to have T omega equals to 1 for an orthonormal basis, let me sketch you a simple argument. Imagine that I look at two operators here. One operator that localizes very nicely in time, between minus a and a. Another operator that localizes very nicely in frequency, between minus b and b. That whole operator is an operator that we know many, many things about. We actually have very good expressions for their eigenvalues. This is work that was done in the 60s by by Landau, Pollack, and Slepian. And we can compute the trace of that operator. It's a compact operator, and it has its trace class, and we can compute the trace, and the trace is exactly the area of the rectangle. That already follows from earlier results by Hermann Weil, but in any case, that's the trace. Now, if we had an orthonormal basis, I mean, then each one of those, each WMN, would be normalized, would be localized around M in time and N omega in frequency, so MT and N omega. And so the sum of the WMNs, each of them is very nicely localized, a little nugget of information. If we only are interested in the information content in the function, then summing only the WMNs which have localization in that or near that rectangle will give us an operator that's very close to that compact operator. So this operator here has to be very close to that self-adjoint operator. And this operator, if we have an orthonormal basis, will have, of course, exactly a number of, it's a projection operator, if we have an orthonormal basis, of which that has, on a space that has dimension, the area of the rectangle divided by the area of the little unit cell by which we are jumping. So we find that up to smaller factors, 4ab over t omega has to be equal to 4ab, so t omega has to be 1. So that's that localization property. So I'm back to the Balian-Low theorem. I've justified that I could look here at parameters 1 and 1. And the fact that these integrals must diverge will follow from the following theorem. It will follow from the fact that if I take functions for which both these integrals are finite, then, and I build those WMNs, then I can find a square integrable function such that its inner product with these things is very, very small. So clearly, I can't have an orthonormal basis. Now, how can I do that? Well, it uses a very elegant argument that mixes time and frequency in an interesting way. So let me, for functions that are nice, define a mapping from L2 of R to some Hilbert space by chopping the function into pieces, integral pieces, and stacking those in a second variable in different Fourier components. It's very easy to see because of, this is going to be periodic in T. And if I change periodicity, if I change to S plus 1, then I can absorb that in K at the cost of producing a 2i pi t factor. So you have these these functions have these very funny periodicity relations. Periodic in one variable and periodic up to phase in the other. On this set of functions that have this periodicity, we define this inner product. We have a Hilbert space. And my first claim is that this operator I have defined is a unitary operator. Okay, how can I see that? Well, let's take a if you take a windowed Fourier transform, then in fact, just little algebra showing, using all these translates and modulations, show that this translating and modulating results in a phase factor in S and T with coefficients m and n in the exponent times the transform of the window function itself. So all this stuff here, the windowed Fourier transform, just becomes a simple phase factor. Now, I can do this, of course, with a very, very simple function. Remember, if I take the function, the characteristic function of 0, 1, then I have an orthonormal basis of L2 of R, namely just the Fourier series on each integer piece. If I do this on that function, this will become 1, and I do have a nice orthonormal basis for hg, which is just, after all, L2 of 0, 1 squared with a funny extension property. So it maps an orthonormal basis to an orthonormal basis. It's a unitary operator. Great. I also claim that if a function is smooth and has good decay, then its image will be continuous in the ST plane. So let me show you that. So I'm in this Hilbert space, the space of functions that are square integrable on 0, 1, and that have this kind of extension property. And suppose that this function is strictly positive. It's nice and smooth, and it's positive on the square. It's a continuous function on the square, and it's positive. Then its absolute value is positive too. And absolute value has this periodicity. So what it means is that I can write that I have that the function times is equal to its absolute value, and I get this exponential, where phi itself has to be continuous too, because I just get it by dividing this function, by multiplying by 1 over f, and since f is bound below by a positive constant in absolute value, this is continuous, and so phi is going to be continuous. The properties I have here involve that if I move t by 1, I have to move phi st by some integer. If I move s by 1, then I'm going to move the phase of f, which is phi, by some integer plus t, the t that I get there. Okay, and now what we have done, what we're really building is showing that we have a little circle bundle that is having a topological obstruction to the construction that I just made. So what I'm going to do is I take this function phi of s plus 1, t plus 1, I'm going there in 2 different ways. First augmenting s and then t, or first augmenting t and then s. And you get 2 expressions in the right-hand side. And I have here L of t and k and so on, but remember, these are integers, and they're continuous, so they have to be constant. And so they drop out, phi st is common, and I end up with t equals t plus 1, which of course can't be true. The contradiction lies in my assuming that I could, in fact, because of this, define phi as a continuous function. And I can't. I mean, you can't comb the hairs on a circle. And so you must have a 0. And that is the essence of this theorem. I mean, if you now take a nice W, which has nice decay and so on, then its Zach transform is going to be a smooth function. That's easy to prove. And then once you have a smooth function, this whole computation that I did earlier shows that the original sum of coefficient squares is giving me an expansion where I get multiplication with a function that has a 0. So if I just take a function that is localized near that 0, then the result will be very small, and I'm done with my theorem. So I cannot possibly get an orthonormal basis. So this was a theorem that was well known. I mean, so what happens if you look in terms of t and omega, then what you get is that if t omega is bigger than 1, you do not span. You can have orthonormal basis on t omega equals 1, but not with nice window functions. You don't get an orthonormal basis. You can build families, Wn, and if you take t omega less than 1, that give you nice concentration time frequency, and that actually will give you equality in norm. But what happens is that W itself, to compensate for the fact that I take too many functions, has to have norm less than 1. Now, there's very interesting things you can do with these. I mean, you can use them in many applications, and in fact, the orthonormal basis, once you take, you have that your redundancy is 2, you can do very special things, recombining them to get an orthonormal basis that doesn't have good localization frequency anymore. It has positive and negative frequency localization, and that can be useful to analyze signals. In fact, the gravitational detection of gravitational waves was done with such special functions, which we called Wilson basis, and that were constructed by Stéphane Jaffard, Jean Lajournée, and myself in the 90s. But that's a different story. We have understood the windowed Fourier transform. To remind you, I take a window, well localized in time and frequency, and here I take something that is nicely localized around 0 in time and frequency. I may modulate it, and so that brings it to this little nugget bit at a higher frequency. And I may move it, and so on. And so I have a whole collection of these in time-frequency space. For the wavelet transform, what you do is you start with a function that looks like one of these. So it's already oscillating. It's already localized away from 0 frequency. And we're going to, again, we want this time frequency aspect. We want to localize in time and in frequency. So how we're going to do it? We're going to do a different strategy. We're going to squeeze or stretch the function. So squeezing it gives us something that has much higher frequency here. Stretching it gives us something with much lower frequency. And then I have to move those around because now I'm still looking only around 0. If I move those around, then I'll have to move the very narrow ones over tiny steps and the very wide ones over big steps that are adapted to its width. And so I get a different kind of lattice for wavelets. Now, why might you think another way of discretizing this is to have alpha k t minus beta l. If you see here, the translation is really by if alpha is bigger than 1 and k is positive, then I have a very narrow function, and I translate by this integer multiples of a very small step. So why is this a good idea? Well, the first thing you do is that, well, if I take a function like that and I look at this continuous transform where B and A are continuous, just like in the windowed Fourier transform, I also look at it continuously. Well, there is something very similar that is true. You have a reconstruction formula, and it turns out that the reconstruction formula is a formula that had been discovered and used by Calderon in analyzing singularities and harmonic analysis. Another thing that suggests this might be a good idea is that we are treating frequency in a very logarithmic way here. And that's a good idea because that helps preserve localization. You know, of course, that if I look at a function and its Fourier coefficients on a function on 0, 1, that smoothness of the function results in decay of the Fourier coefficients. And decay of the Fourier coefficients with smoothness. But you see, I'm losing quite a bit here. Ck gives me nk, and here I have to have k plus 1 plus delta to get back to Ck. So I'm losing quite a bit. And in fact, the reason for that is that the phases are very important. Another way of seeing that phases are very important, the localization of what's happening is important, is that you can have functions that are of some power of which is integrable, and then by just tweaking phases of that function, all of a sudden you can make its singularity, for instance, at 0, much worse. So the Fourier series and the Fourier transform, we are used to them being so nice in L2, but as soon as you leave that framework, they're really not so great. Another way of seeing that is if I just take a function and I decide to reconstruct it from its Fourier series, but change the phases. That operator, if you give me a sequence of phases that I just throw in, can be a lousy operator. It can be unbounded between LP spaces. It can take you from one CK space and map you to another one. I mean, it's really nasty. But we've known since the 30s, since the work of Littlewood and Paley, that if you do it in a slightly less random way, that if you take your coefficients in exponential blocks. So you take the ones that are around the same frequency together, and you do that in an exponential or logarithmic way, if you, then you don't have these things. An operator that does this kind of stuff with the phases will preserve local behavior. You will not generate worse singularities. You will keep track of local smoothness. So for all these reasons, this is a good idea. So then you can ask the question that we had in the time frequency in the windowed Fourier transform. Do there exist choices for which you have an orthonormal basis with nicely localized generating functions? And of course, if you don't care about how well localized they are, again, you have an answer. We've known for over 100 years that the Haar basis, when you scale and dilate it like that, gives you an orthonormal basis. You can also, in frequency, localize on a band and make orthonormal bases. But the Haar basis, of course, since it's discontinuous, has bad decay in frequency. The Shannon localization gives you bad localization in time. But it turns out, and that was the big surprise of the 80s, that there are good possible choices for psi. This was the first one that was recognized as such in the literature, although it later turned out there was an older one in the literature that was hidden, but because it hadn't been spelled out that it had these properties. It was constructed by Yves Meyer, who was the Abel Prize winner a few years ago. The first construction he made was kind of miraculous. I mean, he had set out to prove, he had picked up on the subliminal belief in some joint papers of Alex Grossman and myself that this probably would not be possible, since it's not possible for the windowed Fourier transform. And then he set out to prove it. And after some miraculous things, all of a sudden he had an example. That family of example became better understood through joint work with Stéphane Malat, because we understood that this is this idea of a hierarchical successive approximation. And let me sketch that for you right now. So that's the concept of multi-resolution analysis. So imagine that you have a space, part of L2 of R, that's invariant under integer translations. I'll give you an example very soon. And imagine that I have a nice function in that space so that it and its integer translates generate that space. Since it was invariant under translations, it's reasonable to assume that there might be such a function. I am also going to look at scaled versions of this space, namely, I'm going to scale my function and look at its integer translates or translates by scaled amounts and look at their span. So I have all this hierarchy of functions that are translated by integers, then I squeeze the function and translate it more often, squeeze it more and so on, or I stretch it out, just like we were doing earlier. And I'm going to assume that V0 is part of V1. That's an assumption to which we'll have to come back. So what that will mean is that the function phi, which was sitting in V0, is going to be also in V1, which is spanned by the translates of its own squeezed version. And so we have a lot of very special approximation spaces that are embedded in each other. And we are assuming that if you go finer and finer and finer, you typically have everything. So, well, I'm just saying assume, assume, assume. I can assume till I blew in the face, and I can end up with the anti-set. So, an example, take square integral functions that are continuous, piecewise linear, and that have breakpoints only at the integers. That's invariant under integer translations. There is a very nice function so that it and its integer translates will generate that whole space. So, fine. Now, how do we get wavelet bases? Let's assume for a moment the phi 0 and are orthonormal. Phi and its translates are orthonormal. Then, since phi itself, remember, phi here, this phi, was sitting in V0. And V0 is part of V1, and that's the case for this example. I mean, V0 is things that break only at integers. If I look at functions that are generated by this thing squeezed, then it can break at the half integers as well. Well, clearly V0 is in V1. I mean, any function V0 has the good taste of breaking only at even multiples of half integers. I mean, so. And this was just translates up to scaling. So it means that you have this kind of relationship between phi and its translated dilates. And so its integer translates, likewise, can be written as a linear combination of the phi 1n. And the orthogonality of the phi 0k will lead to, it's very easy, to a special kind of identity that these HNs, these coefficients, have to satisfy. Fine. Once you have that, you can also, since this is really a kind of discrete convolution, once you go to the Fourier side, it becomes a multiplication of a multiplier with phi hat of xi over 2. This was phi of 2t translated, so you get here a phi hat of xi over 2. So this is just some little bit of algebra that you have to go through. Now, V0 is generated by integer translates of a function. V1 is generated by half integer translates of a function. So it's kind of twice as big. So if you look at anything that lies in V1 but is orthogonal to V0, you get a complement space that feels like it's the same size. And in fact, what you can prove is that you can build explicitly some linear combination of those generating functions for V1 that turns out to be orthogonal to V0. And because you see the coefficients that I have here, I'm going to call them Gn later, they are going to satisfy the same kind of identity as the Hns do. And as a result, psi and its translates will be orthogonal. And so I automatically will have built in V0 this subspace W0, in V1 this orthogonal subspace W0 to V0, and together they make up V1, and both of them are generated by the integer translated form function, phi and psi. And the same thing happens at different scales. This whole thing is built to be scale invariant, so I can do that at different scales. And if you do see, you see that V3 is going to be the sum of this plus V2. But V2 was W1 plus V1, and V1 was W0 plus V0, and V0 is W minus 1 and V minus 1, and so on. So you have this whole concatenation. And what that means is that if I take any function and project it on the very fine space here, I get the projection on a very coarse space plus this sum of its decomposition, each one in this complement spaces. I see this actually mentally as an enormous zipper. I mean, where the way of going from one stat and so on, the pull of the zipper is this going up and down by doing basis transformations. And we know that on the left, as j tends to infinity, we get to all of L2. On the right, as j prime goes to infinity, so we have projection on a smaller and smaller space, we get 0. And so we have decomposed our function to wavelets. So it's a very natural kind of construction. So, and decomposing into wavelets is easy because you pull your zipper all the time. You go from, because the phi's in your Vj space can be expressed in terms of the basis of Vj plus 1, and the psi's as well, you just have a very easy transition going from one to the other. So it's a very natural, and you see it had the form of a convolution and then a subsampling. So n minus L would have been some kind of convolution, and then we only take the even samples. So convolution and subsampling, it's very, very simple. And so you can do that decomposition very, very easily. There's one slight problem with this, namely, we were starting by saying if the phi 0 n, phi and their integer translates, are orthogonal. Well, in the example we had that I showed you, these splines, they were not. Now, can I deal with that? Yes, I can, of course. What does it mean that they're not orthogonal? If you express it in terms of the Fourier transform, it means that here, I made a mistake here. This should be between 0 and 1 instead of minus pi and pi. This sum is not a constant. But I can give it a name. And I can then, that function, since it's has a Fourier series, I can use those constants to find another function v0 using those. Or, in other words, I define a little phi hat this way. It's still in v0, it translates span v0, and if you work it out, it and its translates will be orthogonal because this sum, by the very construction of little phi hat, is going to be 1. And so you get delta k 0. So this is the function I should be using instead of the b spline. Fine. So these are the coefficients that I should be using. But that function has infinite support. So I have dealt with a very nice way of using this decomposition with these very nice coefficients in there, but they now have infinite support. Who cares? You just truncate, you say. After all, they have exponential decay, they're small at some point, they're small pretty far out, but still they're small, you truncate. But that's where I didn't like this approach, because Wavelet Basis, I showed you, I mean, I just waved my hands, but they're very useful because they have very special properties. They have this logarithmic treatment of frequencies. They make it possible to look at absolute values of coefficients to assess local smoothness and so on. And all those depend on the mathematical properties of that basis. If you start truncating, then you're working with objects that don't anymore have these. You don't know what you're dealing with. So so as I said, we can characterize local smoothness by means of the decay of wavelet coefficients. We can see whether, if we are in an LP space, then we can just truncate. I mean, we can put to 0 coefficients that are very small, and we're still in the LP space. If you don't have that, then, I mean, many of the operations you'd like to do as an applied mathematician are no longer controlled. I mean, if you're not working in L2. So the question is, could you have it all? Could you have all this beautiful MRA, the easy algorithms, and all those unconditionality, all those beautiful mathematical properties? And the answer, indeed, it turns, is yes. I mean, I'm not going to go into technicalities of that, but that's what Jill was saying that I was known for. You can start just from the HN. Remember, we had properties for the HN. And you can build the HN in such a way that you can then milk out everything else back again. So you build functions for which you don't have an analytic expression. You have an algorithmic way of building them, but you can prove smoothness, you can prove unconditional basis, and all those beautiful things. Here is a first example. This is a function that corresponds, that is supported between, the lower axis is meaningless here. It's supported between 0 and 3. Remember, Haar was supported between 0 and 1. This is supported a bit bigger. This is a slightly smoother function. You have the wavelet here on the left, this corresponding scaling function on the right. See, these functions don't particularly look very nice. I mean, this is actually, this is almost C1, not quite. But you can make something that are much smoother. Now, in practice, these beautiful properties lead to very interesting applications. So let me show you graphically what that means. If I take this image, I mean, decomposing into the coarser scaling functions and the wavelets is like making a local average and then looking at the difference between the thing and its local average is like a local difference. So when you have it in two directions, you have to do it both horizontally and vertically. So if you average in both directions, you get an image that is the same, just smaller, because we have subsampled. But you also have, and now because I have to do it in two directions, I have differencing and averaging, or averaging and differencing, and differencing and differencing. And what you see here, my convention originally was that I went from 0 to 255, 0 all black, 255 white, and it's the same here. Once I start taking differences, I can become negative. Oops. I can become negative. And so then I make my convention that middle gray will correspond to 0, and negative will become dark, and white will become large and positive. And so you see most of my image is middle gray here. Most of the coefficients are very small. And that has to do with the fact that where things are smooth, wavelet coefficients are small. I see vertical edges, especially here, horizontal edges, especially oblique things. And I have to repeat this at many scales. I mean, that's the thing that you do with wavelets. And you can visualize that content if I just take and reconstruct without taking into consideration what I get from the wavelet coefficients. This is scale after scale what I get back. And I can understand this by looking at two different parts of the image. Okay, so these are two different parts of the image. One where the function is nice and smooth. The other where it has sudden transitions. Remember, we wanted sudden transitions, well represented, and we wanted smoothness, well represented. So let's concentrate on the patch of scale and construct it. I mean, yes, there was content in the low frequencies, but I need more and more, and I need to keep adding detail to get it perfectly. But if you do the same in the sky, actually, I don't know how well you will see it in the room, but there's only a little bit that gets added in this coarse scale. But from now on, there's not much. I could just as well have put all those coefficients at fine scales to 0, because they're very small. And by doing that, I'm not sacrificing anything, because I know that I have these good properties of the wavelets. Okay, now standard wavelet bases are, to be honest, not ideal for images. Why not? Well, when I go in frequency in one dimension, so here at the top is one dimension, to the lower I have, essentially I look at this, and the differences look at these two pieces there. If I do it in 2D, then going from this to the lower dimension misses out this whole ring. And if I look at differences here and differences there, that covers those 4 corners, which are already very different directions in my image. If I look at differences in one direction, but averages in the other, or the other way around, I have these very wide ranges of angle too. Not as bad as the 2 corners, but... and in fact, you kind of see that in this decomposition. You can see that where I have a transition here that's mostly horizontal, I actually have to deal with that with many wavelet coefficients. I mean, while in fact, if I were a little bit more well organized in direction-wise, I could do that with much fewer things. And so that is something that people do with curvelets. So wavelets in 2D are ideal when you look at things that are point singularities, point things. So in astronomy, in observational astronomy and compressing of those data, wavelets have made an immense difference. Every time I meet an astronomer, they tell me what the differences have made to their field. Well, those are stars. I mean, of course, they do have some structures too, but those are not long strands of hair. I mean, so you can, by trying to divide better in the frequency domain, get what are called curvelets. And those have been proposed. and are useful in order to do that. Efficient implementations do typically not correspond to orthonormal basis. There's a nice construction by a postdoc of mine and a former student of Yves Meyer, Sylvain Durand, that does something for a different splitting up in time frequency, but it has some problems. Another thing is that curvelets have is that in order to do the optimal thing for images with sharp edges, you should really, at low frequencies, be okay with wide angle and so on. But as you go to higher and higher frequencies, you become more and more narrow in your frequency range. And it is called a parabolic scaling. Typically, every double, you shouldn't really refine the angle every doubling, but every 2 steps. So from here, I refine, and then I keep that. And at the next level, I would refine again and keep that for 2 steps, and so on. Now, this is again something where very recently, and here I come to the advertised result by a young collaborator, it turns out that there is an insight we had from the one-dimensional thing that makes it possible to do something much nicer in high dimension. See, I told you that if you have HN, GN, they allow you to reconstruct multi-resolution analysis. And convolution with these and subsampling lead to this decomposition of the finer space into the basis for the 2 coarser space. That was my zipper going up and down, these changes of bases. But you can use this in order to split any space that's invariant under integer translations, under integer shifts. It doesn't have to do anything with wavelets. It doesn't have to do anything with the HN, GN. You can always take the appropriate combinations and then just of those functions take only the even translates, and you will generate a nice splitting of your original space. I call this the cutting lemma. And the cutting lemma it always works, but it's only useful if what you're done makes sense. I mean, since I was convolving, it's like multiplying with a multiplier on Fourier's side, and I'm multiplying by something that's periodic. Well, if this thing is very wide and I'm going to multiply it by cutting out periodic pieces, I'm going to get something very awkward. So it better be that this thing is well localized so that my cutting takes a little piece of it and then the remainder of it is also something coherent. It's not kind of a mosaic. Well, you can do similar cutting lemmas in 2D, and lo and behold, they work to be useful only if you dissect frequency after every other dilation step. So here are some figures from a paper by Wei Zhu that will soon be on archive. It's not yet because I've been remiss in doing the revisions to it. I'm sorry. I mean, it's my fault. Where you see that he's using the cutting lemma to break up things, cutting lemma to break up regions into smaller regions and even smaller ones. And he's used those. I mean, here you see, this would really, if it were ideal, and the corresponding wavelets. So this is a Shannon case, but in 2 dimensions. And you see that in practice, there's some leakage elsewhere. But if we start looking at the wavelet functions in detail, then you see this is the Shannon case, the sharp cutoff. Here is the basis case with after 2 of these splittings, and it's very nicely localized. You have a little bit of ringing, but much less than in the Shannon case. And here are results using those for images. So here I have an original image with lots of features that are designed to do well under curvelets. We are compressing quite a bit, but we're compressing by the same factor in all these examples. This is what we get with the standard wavelets, and you see that vertical directions, diagonal directions are okay, but when you change from those 2, you don't do as well. This is what, this is what curvelets give. This is the hexagonal wavelet basis, the one with the cutting. Similarly, I have another example here. Curvelets are doing extraordinarily well at long strands. They don't do well at very localized things. But this nice basis that Wei constructed using a cutting lemma in 2 dimensions is an orthonormal basis, but it gives the good localizations that you in long strands from curvelets, but it still is good at local features. And my time is 0, so I should stop.
Thank you very much. We do have a few moments for some quick questions. If you do have a question, though, please come to the mic.
I guess.
Okay, well, let's thank our speaker again. Beautiful lecture.
Excuse me. Excuse me, I have a small question.
Okay. Oh.
So when you are localizing and cutting the pieces, what do you do about the boundary? Are you losing any things?
So when you reach the boundary, you have to do a special adapted situation. So in multi-resolution analysis, the reason wavelets do so well for local smoothness is that they are, the multi-resolution spaces contain low-order polynomials. And if you do low-order polynomials, you zero out low-order polynomials, then you zero out the low terms in the Taylor expansion. That gives you the decay of the wavelet coefficients. If you have a boundary, then that means you have to build your multi-resolution in such a way that you contain the polynomials with that boundary. And so you have adaptive multi-resolution analysis and so on. And there are techniques for doing that.
Thanks for that great question. We'll probably have to take other questions after this lecture. Thanks.